Today, we want to review exponential functions. We're going to be looking at an exponential function today in a very similar fashion to the way we looked at the linear function yesterday. So let's begin with a function g of x with a table of values. So here we have x and g of x. We have negative 4, 3, 0, 6, 4, 12, 8, 24, 12, 48, and 1696. So what we want to notice is, first of all, one of our x's is 0, so that's a good place to start. We always like having our starting. We always like to start with the y-intercept if we've got it. We want to look at what kind of pattern we see in the numbers, and when we go from 3 to 6, and then from 6 to 12, we should, instead of thinking we added 3 and then added 6, we should think we multiplied by 2. So we see this pattern of repeated multiplication by 2. So this is how we know we're dealing with an exponential function. So here's how we know we're dealing with an exponential function. We have this pattern of repeated multiplication, and we have multiplication happening at regular intervals. This is happening every 4 units. So we want to explain why we know that g of x is an exponential function. We could see that g of x has a pattern of repeated multiplication. So that pattern of repeated multiplication is what's going to give us our exponential function. G of x has a pattern of repeated multiplication. Next, we might want to be more specific about what's going on. So let's write a sentence describing g of x. Let's write a sentence. And we're going to follow the same kind of pattern that we followed yesterday with the linear function. We're going to state where things start. We're going to talk about how the function is changing. And then we're going to talk about how often the function makes that change. I always like to start with a y-intercept if I have one. So I'm going to start with that. I'm going to say g of 0 is equal to 6. That's an indication of where things are started. Then we're going to describe what's going on. So we're going to say, and g of x is multiplied by 2 every 4 units. So here's a sentence describing g of x. This is why we like linear and exponential functions. They have a pattern of a repeated operation, and that makes a sentence describing them nice and straightforward. Now that we have a sentence describing our function, we'll want to be able to write an equation describing the function. So let's write an equation describing g of x. And we're going to do this similar to how we did the linear function yesterday. We're going to write where it starts, we're going to write how it's changing, and then we're going to write how often it makes that change. So let's write g of x. When we have the y-intercept, we use that for a starting place. It's our favorite starting place, right in the middle of the axis, or right in the middle of the x-axis is the y-axis. So let's start there. So g of x will start at 6. Even though the table starts at 3, I like to look for where x is equal to 0 and say that's where things are starting. So I'm going to say g of x is 6. And then I'm going to say what's happening to g of x. G of x is multiplied by 2 a bunch of times. I'm going to use parentheses around a 2 to say g of x is multiplied by 2. It starts at 6 and it gets multiplied by 2. Then I need to say a bunch of times. And to say repeated multiplication, we use an exponent. So 2 raised to the a bunch of times. In this case, we'll say x over 4. Every time the exponent is a complete multiple of 4, an integer multiple of 4, we have multiplied by 2 that number of times. So when x is 4, the exponent is 1. We've multiplied by 2 one time. When x is 8, the exponent is 2, and we've multiplied by 2 two times. When x equals 12, the exponent is 3, and we've multiplied by 2 3 times. So here is an equation describing g of x. The next thing we can do is use our equation to evaluate the function and solve equations. Given an input, find an output. Or given an output, find an input. So I could say find g of 10. Show your calculations, round your answer. I usually say to the nearest 10th or the nearest 100th. So to find g of 10, so first of all, if we look at the table, in this case, the 10 is an x. So this 10 is going to go in for an x. So if we put a 10 up in here, in between, we see the 10 is between 8 and 12. So we should expect g of 10 to be somewhere between 20 and 48. But now that we have an equation, all we have to do is plug 10 into the equation. So if I want g of 10, I just take 6 times 2 to the 10 over 4. So I just take the 10 as the input. And I can type this in my calculator exactly like I write it. This is why I write things in single line syntax, because my calculator does some single line syntax. So I'll do 6 times 2 to the 10 over 4. We get 33.9. We were expecting something between 24 and 48. We got 33.9, which is between 24 and 48. And so we're pretty confident that we want to say 33.9. By writing or typing the 6 times 2 to the 10 over 4, this counts as show your calculations. So this part right here, that is the show your calculations portion of your answer. Here we took the 10, plug the 10 in, and find the output. One of the points on the graph is 10 and 33.9. Just like yesterday, I can also play this game in reverse. I can give you 10 as an output and ask you to find the input that leads to a 10. So I could also put a 10 down here, so as an output, and ask you to find the input that leads to it. 10 is between 6 and 12, so we should expect a value of x between 0 and 4. 10 is closer to 12, so we should expect our output or our input to be closer to 4. So another question that I could ask for this function, just in the basic usage category, I could ask you to solve g of x equals 10. And then I'd say, show your calculations. Or round your answer. So in this case, the 10 is not the inputs, because the inputs go in where the x is. The 10 is on the other side. What x do we have to put into g of x to make it deliver a 10? So now we'll say 6 times 2 to the we don't know over 4 has to equal 10. Now 10 is showing up as the output. In this case, we have a pretty strong advantage because this came from a table. We know that x should be somewhere between 0 and 4. So let's come at this a different way. We know x is between 0 and 4, and probably closer to 4. So we could do inverse operations in reverse order involving logarithms, but let's suppose that we don't need exact answers because I just said round your answer. We know that the number is something between 0 and 4. So let's try some things. I'm going to make a table of values and just keep going until I get closest to 10. So I know that if x is equal to, oops, wrong color. If x is equal to 4, then g of x is equal to 12. When x is equal to 4, g of x is equal to 12. And so that's too high. So I'm just going to grab my calculator. When x is equal to 3, I need 6 times 2 to the, so 4, if I do 4 over 4, that gives us 12. If I do the same calculation but with a 3, that's 10.09. If I do to the 2 over 4, that's way too low. So now I've narrowed it down even more. So I know I'll get exactly 10 if I'm between 2 and 3, but closer to 3 because the 3 came out very close. So now we know x is between 2 and 3. So now I've got x between 2 and 3, and it's closer to 3. So it's going to be 2 point something. If I try, I'm going to try close to, very close to 3. I'm going to start with 2.9 divided by 4. And I get something less than 10. So at 3.0, I'm just going to repeat down here. So this is us going for the integer part. At 3.0, we get 10.09. At 2.9, we get 9.992. So now we can say that x is between 2.9 and 3.0. 0.92 is 800ths away, and 10.09 is 900ths away, so 2.9 is closer. So now we've refined this a little bit. X is between 2.9 and 3.0 and closer to 2.9. If I want to go further, so we see this because when we plug in 3, it's too high. When we plug in 2.9, it's too low. We're trying to land on 10. So let's plug in 2.95 because we know we're in between 2.9 and 3, and it's about evenly split. What if we put in 2.95? 2.95 gives us 10.003. And let's try 2.94. And 2.94 is a little bit low. So I just I just split the difference between 2.9 and 3.0. And if I plug in 2.95, we get 10.004. And then since this was high, we'll plug in 2.94, and that gives us 9.986, which is lower than 10. So now we can say that X is between 2.94 and 2.95 and closer. So the 0.004 is closer to 10 than 0.986. This is 4 thousandths away from 10, and 0.986 is 14 thousandths away from 10. So, and closer to 2.95. So if we wanted to, depending on where I said round your answer, X is between 2 and 3 and closer to 3. So the nearest unit, X is equal to 3. If I said nearest tenth, the closer tenth is 2.9. It's 8 hundredths away, where 3.0 was 9 hundredths away. So we'll say X equals 2.9. If I ask for the nearest hundredth, .95 is 4 thousandths away, where 2.94 is 14 thousandths away. So the closer hundredth is 2.95. We can continue this if I said, depending on how much accuracy we needed. I know it's between 2.94 and 2.95, so I'm going to try to split the difference at 2.945. I'm just going to cut it in half again, and let's go for one more decimal place. Start in the middle, and that is too low, 9.995. So I'm going to go up. That tells me to go up. So I'm going to try 2.946. And that's still too low. So I'll just go up again, 2.947. Still too low. Should have been taking bigger steps, I guess. But you'll notice that as the thousandth creeps up, we're creeping up on 10. So looks like we're getting pretty close. Up 18, up, and then, okay, looks like, I think the next one's going to do it. Let's find out. So if I do 2.948, we're above 10.0002. So now I've got an over and an under. So now we can we've refined our answer even further. We can say that x is between 2.947 and 2.948 and closer to 2.948 because 2.948 is 2/10,000ths away because it's 4 decimal places. And then the 9985, that's also 4 decimal places. That's 10,000ths under 10. So the 2.0002 is closer to 10 than 9.9985. So if I asked you to round to the nearest thousandth, we get 2.948 was the closer one. Now, we could have come at this answer much quicker if I wasn't explaining everything as we go along. We would just know that it's it's between 0 and 4 and close to 4. So I would have had 6 times 2 to the 3 over 4. That's too much. And then 2 is going to be too little. So then I just go to 2.5 over 4. 2.5 over 4. Oh, 2.9. I wanted something closer. And that was too low. But now I've got it in between. It's 2.9 was below and 3.0 was above. So I know it's between those two values. So then I add more decimal places. I always just start in the middle. That's too high. And you're looking for when you have something in the hundredths that's too high and then something that's too low. Then you figure out which one is closer. But you know it's in between those two. So you just keep going until you find the one that's the two that are closest, one above and one below. If I had to go further, now I know it's between 2.947 and 2.948. If I have to do this again, I'll just insert a 0.5. I'll split the difference. That's too low. And then I'll just start going up until I find that's too low. So now it's between 2.9478 and 2.9479. The 9479 is 0.0000006, so 600 thousandths, but the 99989 is 1100 thousandths, so the 2.9479 is closest. So it goes a lot faster if we're not talking about and writing all this stuff down. So this is what we want to do because this is the best thing that we have in math. We just guess. But we don't just guess randomly. We guess intelligently. We look at what we have and we just test our hypothesis. We can also solve this by doing inverse operations in reverse order, but we have to remember our logarithms. So x gets turned into a 10. The first thing that we do in this expression is we divide by 4. The next thing we do is it becomes the power of 2 because exponents go before multiplication. So I'm going to say 2 to the instead of to the 2. And then the third thing that happens is we multiply by 6. So our plan for solving to turn 10 back into an x, first we'll take the 10 and we'll divide by 6. That's the inverse of multiplying by 6. Second, we'll take the log base 2 of whatever we get. And third, the inverse of dividing by 4 is multiplying by 4. So I'll start with a 10. and divide by 6. So 10 divided by 6 is 1.667. I'm going to write that down for notes, but remember, you're not writing this part. This part shows up on your calculator only. The next, I need to do the log base 2 of 1.667. So we have to remember our change of base formula. So that means we'll do the log, the calculator log of 1.667 divided by the log of the old base 2. So do the log. Now, I don't want to round this off, so I'm just going to put second answer, because my calculator right now has a 1.66667 button on it. And I'll divide that by the log of 2. And we're at 0.7369, 0.737 we'll call it. And then we take the 0.737 and do the last operation. We multiply by 4. And that gives us what we're looking for, 2.948. I should have rounded the nearest thousandths. Notice that this is the same thing that we got when we were guessing and checking. So this problem was about looking at a table of values for an exponential function, writing a description of that exponential. First of all, knowing how to identify from the table the exponential function, writing a sentence describing what's going on in our exponential function, writing an equation for the exponential function based on that sentence, and then using our equation, either to take an input and find an output, or take an output and find an input. All right. There are lots of ways that we can find exponential functions. So we're going to have another round of exponential functions tomorrow, a lot of ways we can describe them. The reason that I like this is that notice that we did not need a calculator to describe what was going on in the function. Multiplied by 2 every 4 units. Start at 6, multiply by 2 every 4 units. That gives us plenty to work with. All right, that's going to do it for today. I just wanted to do this one problem. Make sure you check out the final series of quizzes on the old Canvas. Some of this may be relevant to those problems. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.